Hello and welcome to this brief presentation looking at inverse Laplace transforms but using partial fractions. This presentation will review different types of partial fraction and the conditions to be satisfied. It looks at the solution methods to solve for the constants a, b's and c's etc. in the partial fractions. There are three methods used: substitution, comparing coefficients and the cover-up rule. And there'll be worked examples and there'll be tutorial questions. It should be said that this presentation does assume you have some understanding of the use of partial fractions. We use partial fractions when we're solving inverse Laplace transforms to make the transforms into standard form, and the table over the page relates to the standard form inverse Laplace transforms that we're conventionally using. This first part of the table of our inverse Laplace transforms. I've reviewed these in previous presentations, so I won't review them here, but basically on the left hand side we have the Laplace transform in the S domain, and on the right hand side we have the inverse Laplace transform, bringing us back to the function of time, the T domain. This is another part of the inverse Laplace transform table. Okay, we're looking at the three types of partial fraction that we can encounter. The first one is a linear factor. This is where we have a function of x over linear terms. In this case I've got an x plus a, that's a linear factor as it's termed, it's an x to the power 1 effectively. So the form of the partial fraction would be a over x plus a for that bracket. If I had another bracket, the x minus b, then we would have plus b over x minus b as a second partial fraction. And if we have a third bracket, x plus c in this case, we would have then a plus c over x plus c. Okay, so for three brackets, linear brackets, we have three partial fractions. If we only had two linear brackets, we would have just two partial fractions. Repeated linear factors. This is where we have a function of x divided by, in this case, x plus a to the power of 3, a cubic here. That would give us a solution form of a over x plus a plus b over x plus a squared plus c over x plus a cubed. Okay, so three terms there increasing in their power. If we'd only had a function of x over x plus a all squared to begin with, we would just have the a and the b terms only. The more complicated functions, the quadratic factors, are where you have a function of x divided by, in a bracketed term here, we have an ax squared plus bx plus c format, and that cannot be factorised. That makes it a quadratic factor. It's also shown a linear factor here as well. So the quadratic factors are more complicated. The solution of the form of the partial fraction is ax plus b over the ax squared plus bx plus c, and in this case, because we've got the linear factor, we put c over x plus d. But in this presentation I shall not consider quadratic factors, just linear factors and repeated linear factors. There are two conditions we need to be careful of, important conditions we've got to satisfy before we undertake our partial fraction process. The first one is that the numerator must be at least 1 degree less than the denominator. So what that means is, if you look at the numerator, here we have 4x minus 5, and looking at the denominator we have x squared minus x minus 2. The numerator is x to the power 1, don't write the ones, but x to the power 1 is the numerator, and the denominator is x to the power 2. So it satisfies the condition that the order of the numerator, the x to the 1, is lower than the order of the denominator. In this instance here, this example here, we've got 2x cubed plus 3x squared minus 3, all divided by 2x squared minus x minus 1. This does not satisfy the condition because we have a cubic on the numerator and a quadratic in the denominator. You'd have to use something like polynomial division here to reduce the order of the numerator to lower than the denominator. And the other condition we look for is the denominator must factorise. So we try and factorise the denominator if it's not already factorized. So for example, x squared minus x minus 2 does factorize into two linear factors of x minus 2 and x plus 1, and 2x squared minus x minus 1 does also factorize into 2x plus 1 and x minus 1. Okay, if they don't factorize, we're left with a quadratic factor to solve. There are various methods for solving the constants, trying to find the constants a, b and c, or whatever, however many we have. There's something called substitution, which is used to solve all linear factors and the highest power repeated linear factor. There is the equating coefficients of the powers method, and that solves all partial fractions, linear, repeated linear, and quadratic factors. And there's something called the cover-up rule that's used to solve the linear factors and again the highest power of the repeated linear factor. It's very much like the substitution method, but in a slightly different format. So we're going to look at two examples to try and show you how partial fractions can be used to simplify Laplace transforms. We'll be using the variable s now instead of x, but it's just a change in notation. So example 5, we're asked to solve and find the inverse Laplace transform of 2s minus 3 over s open bracket s minus 3 in a bracket. Now that's not standard form, you won't see that in a table. So we're going to try using the partial fractions approach. So the first thing we need to do is be aware of the checks. The first thing, is the numerator lower ordered than denominator? Well, yes it is, because the numerator has an s to the power of 1 effectively, and the denominator has an s squared. If you expand the bracket you get s squared minus 3s, so that's satisfied, and it's already factorized for us in the denominator. We've got the s minus 3 already in brackets. So these are linear factors, so I would write this now as solution as a upon s is my first partial fraction, plus b upon s minus 3. Those will be my two partial fractions. So I need to solve for the a and the b, and then from there I can hopefully put the function to the standard form and find the inverse Laplace transforms. Okay, what we're going to do to try and simplify this function is to multiply throughout by the s times s minus 3 in brackets, which is the denominator on the left hand side. So every term now is going to be multiplied by that. If we multiply the left hand term by that, we will see that they cancel top and bottom, so we end up on the left hand side of our expression with 2s minus 3. If I multiply the first term on the right hand side, the a by the s open bracket s minus 3, the s on the top cancel with the s on the bottom to leave with a times s minus 3. And if I multiply my second term by the s open bracket s minus 3 term, we can see that the s minus 3 cancels top and bottom to leave me with the plus b times s. So now I've got all my terms onto one line effectively by doing that. To solve for the constants, the a's and the b's, what we do now is choose a value of s that makes either the a term go to 0 or the b term go to 0. So for example, if I let s equals to 0 and I put now s into all the expressions, I will find that the b term will disappear and I'll be able to solve for the a term. So that's what I'm going to do. So 2 times s will now be 2 times 0, so that term will disappear. Take away 3, so on the left hand side I get minus 3. And if I go to the right hand side, put in 0 and I've got s there, I get minus 3 times a, and as I said, the b times 0 term disappears. So basically dividing both sides by minus 3, I find that a is equal to 1. So I've got the value of constant a. To make the next term go to 0, if I make the value of s 3, then the a term will disappear on me, so that's what I'm going to do now. S now is equal to 3, so put a 3 where you see an s, and I get 2 times 3 gives me 6, take away 3 gives me 3 on the left hand side. On the right hand side I put the 3 into the a term, that will disappear because 3 take away 3 is 0, so the a disappears and I end up with 3 times the b. So basically in this case 3 is equal to 3b, or b is equal to 1. So in this particular case, it doesn't always work this way of course, both the a and the b have worked out to be the same value, which is 1. So now I know that my 2s minus 3 over my s open bracket s minus 3 fraction can be written in partial fractions as 1 upon s plus 1 upon s minus 3. Just copying that line through to finish off example 5 here, and repeated the line here at the top of the page. What I can do now is take my inverse Laplace transforms of these functions. Taking inverse Laplace transform of the 1 upon s term, if you go to your standard tables, you will see that actually gives me a function of t of 1. And if you look at the inverse Laplace transform of 1 upon s minus a, go to your standard Laplace transform table, you'll see the function of t is e to the at. In this case, the a is going to be 3, so e to the 3t. So I found my function of t by taking my inverse Laplace transforms, but to do that I've had to use partial fractions to get the inverse Laplace transforms into standard form. Look at one more example, example 6 here. I'm given a fraction of 5x squared minus 2x minus 19 over x plus 3 times x plus, start again. Looking at example 6 here, I'm asked to find the inverse Laplace transform of the function 5x squared minus 2x minus 19, all divided by x plus 3 in a bracket and x minus 1 all squared. Again, doing our quick checks, the numerator has to be lower order than the denominator, which it is, because on the numerator I have an x squared, and if you expanded the brackets on the denominator, you would find we get an x cubed, so that's definitely true. And we can see quite clearly the denominator of the fraction has already been factorised. So our checks are complied here. What we've got here, though, is a linear factor. The x plus 3 is a linear factor, and we've got a quadratic factor. The x minus 1 with the squared outside is a quadratic factor. So when I write down the function that I'm given, and I equate it to the partial fractions, I will get a over x plus 3, that's the linear factor considered, and then for the repeated linear factor I will get b over x minus 1, and then c over x minus 1 all squared. We have pluses between all of these fractions. Okay, so I've accounted there for my linear factor as the a constant, and then the b and c relate to the repeated linear factor. What we're going to try and do now is make a common denominator, similar to what we did in the example 5. So on the left hand side I've got my x plus 3 times by my x minus 1 all squared. So what I'm going to do now is write all of the fractions, the a, b and c, all over the x plus 3 and x minus 1 squared fraction, because once the denominator is the same on either side of the equation, they effectively cancel out and I'll be left with the numerator. So just be careful here now. Against the against the a, I will get x minus 1 squared. Okay, that then means I can write it over the x plus 3 x minus 1 squared function. Against the b, I will get x minus 1 times by x minus 3. That means I can now write the b over the x plus 3 x minus 1 squared, and it's still really b over x minus 1. And against a c, I will get x plus 3. So again, I can write that now over the x plus 3 x minus 1 all squared, because really that is c over x minus 1 squared. Okay, just take a moment to review that and make sure that you understand that. Essentially, by putting the common denominator on the right hand side, I have to make sure I do not affect the original equation. I must still have a over x plus 3, I must still have b over x minus 1, and I must still have c over x minus 1 all squared. And if you cancel the brackets top and bottom for each of the terms, you'll see I still do. So I've not affected my original question by doing that. Once you have the same denominators on the left hand side and the right hand side, which we do now have, you can simply equate the numerators, and that's what I'm doing here. I'm just looking at the top line of the function, so this line here is basically the top line above. I've called that equation 2. All I'm doing in equation 3 is just expanding some of the brackets. It just makes it easier, you'll see, with the technique we're going to use in a moment, sometimes to have the right hand side expanded. It's not essential to do this, but sometimes it's easy to follow a solution. So all I've done here for the A part of the equation is I expanded the x minus 1 squared. Don't forget it's a binomial expansion, x minus 1 times x minus 1, and that will give you x squared minus 2x plus 1. I've done the same for the b. I've expanded the x minus 1 times the x plus 3, and that will then give you b times by, in the brackets, x squared plus 2x minus 3. I've not expanded the last term because I can clearly see the terms quite nicely. I'm only producing equation 3 to make it easier to understand where the terms are, the x squares and the x's. Okay, in example 6 now we're going to solve for the constants a, b and c. To do this I'm going to use the cover-up rule to solve for constants a and c, and I'm going to use comparing coefficients to find constant b. I can use the cover-up rule for all linear factors or the highest power of the repeated linear factor, so in this example that's constant a and constant c I can find with the cover-up rule. To use the cover-up rule, what we say to ourselves is, looking at the denominator of the a constant, what do I need to make x to make that bracket go to 0? If I make x equals to minus 3, then that bracket goes to 0. So what the rule does is say, okay, cover up this term on the left hand side and put the value of minus 3 wherever you see an x in the rest of the expression. So on the top line you would have 5 times minus 3 squared, take away 2 times minus 3, take away 19, and on the bottom, because I've covered up the x plus 3 bracket, I just see the x minus 1 bracket, so that's minus 3 minus 1, and that's all squared. Okay, if you just follow the arithmetic, just be careful when you're squaring negative numbers. Don't forget when you square minus 3, for example, you get a positive 9. Just follow the arithmetic too, and that will give you a value of a of 2. So constant a is 2. If we apply the cover-up rule for a constant c, we do the same kind of procedure here. We say, okay, what value do I need to make x to make that bracket go to 0? Then we need to make that x equals to 1, and I simply put the value of 1 into the left hand side of the equation, but now I cover up the x minus 1 squared expression, leaving the x plus 3 bracket. So again, putting the value of 1 this time into the numerator, I get 5 times 1 squared, take away 2 times 1, take away 19. On the bottom, because I'm looking at the x plus 3 bracket, I will get 1 plus 3. Again, if you follow the arithmetic through there, you'll end up with a minus 4 for the value of c. So we've got our a and our c constants determined. Now, to find the value of the constant b, I'm going to use something called comparing coefficients. This method works for, I could find all the a, b and c with this method if I want to, because with comparing coefficients we can generate, in this case, 3 equations, an equation for x squared, an equation for x, and an equation for constant. But because I've already used the cover-up rule, which is quick and easy to use, I only need to generate 1 equation to finish off the constants. So in this case, to find constant b, I'm going to go back to equation 3, which I repeated above for convenience here. What we do with comparing coefficients is look at the coefficients, that's the numbers associated with, in this case, the x squared terms on the left hand side of the equation and on the right hand side of the equation. So if I look at the x squared terms on the left hand side, the coefficient associated with the x squared term is 5. So I've got 5 on the left hand side, and on the right hand side, looking at the coefficients associated with the x squared, I can clearly see that I've got an ax squared if I expand that bracket, and I've got a bx squared if I expand the second bracket. So I get a plus b on the right hand side. As we've already found the value of a from the cover-up rule, we know the value of a is 2, we can then rearrange the equation to find the value of b, and b is 3 in this case. So now I've found the values of the a, b and c constants. A is 2, so that's 2 over x plus 3. B is positive 3, and that's over x minus 1. And c is minus 4, and that's over x minus 1 all squared. We're now at the stage where we can find the inverse Laplace transforms of our partial fractions. So I've got 2 upon x plus 3 for my first partial fraction, plus 3 upon x minus 1 for my second one. Now if I look in my inverse Laplace transform tables, that follows the pattern of 1 upon s minus a. So I think I can use that for the first 2 partial fractions. Looking at my third partial fraction, I get minus 4 upon x minus 1 all squared. From my inverse Laplace transform tables, that fits n factorial over s minus a to the n plus 1. So let's look at the first partial fraction. I'm finding the inverse Laplace transform of 2 upon x plus 3. That fits the format of 1 over s minus a. Just as a factor of 2 on the top, and the a would actually be in this case minus 3. So I can write the first term down as e to the ax, in this case x being the variable, e to the minus 3x, and I must multiply it by the factor of 2. With the second term, I've got 3 over x minus 1. That fits the 1 over s minus a format with a factor of 3 on the top. So that would be e to the x, e to the 1x in this case, because a is 1, and then factoring that by 3. Looking at my last partial fraction, the minus 4 upon x minus 1 all squared, that fits the n factorial over s minus a to the power of n plus 1, where a in this case is 1 inside the bracket there, and the n would actually be 1 because it's n plus 1, so 1 plus 1 gives me the 2, so n is also 1. So that allows me to write the term of e to the ax, e to the at, it says in the transform, or e to the ax in our expression, so e to the 1x, and then the t to the n in the Laplace transform would be x to the 1, or simply x in our final solution. All I've done with the last line is just slightly rearranged the last term. So there's our solutions to this problem. Okay, here are some tutorial questions I would encourage you to have a look at. They're based on the previous examples. The answers are given here in the bracketed terms at the end of each of the question. I hope this presentation has been of interest to you, and thank you for viewing.